All right, I think we're going to go ahead and get started. All right, so on the screen here we have kind of the general exam stuff reminder here. So exam 2 is going to be a no notes, non-calculator, closed book, 60-minute exam focusing on sections 2.8, basically through 5.5, all the sections that we have covered in that range. Although, of course, earlier content will be required to do some of the work. Practice exam has been posted in the week's module. The affinity exam has also been posted. So make sure you work through those. The best resource is going to be that affinity practice exam. And the exam is scheduled for Thursday. We're a time range from about 4:30 p.m. to about 10 p.m. Everyone should have already signed up for a specific time in Sign Up Genius. Any questions about how the administration of the exam will run, or any questions about the exam? All right. Throughout the review session, feel free to chime in anytime if you have questions. I will also be monitoring the chat if you prefer to use that. But for now, we will get started. All right, so 2.8 and 2.9, we got started with the idea of generalizing the concept of the vector space. So instead of just thinking about vectors as these vectors in R3 or R2, instead we started to think of them as any object, collection of objects, where we define vector addition and scalar multiplication that satisfy our big 10 properties. So they could be polynomials, they could be matrices, they could be fruit. If we defined addition, defined scalar multiplication, what these 10 properties hold, we would have a vector space. Now in our focus on the course, we worked on subsets, so little subsets here inside of bigger vector space. And the question was, were these subsets actually vector spaces by themselves? And that's what we looked at. And to show that a subset was a subspace, we didn't have to show all 10 properties held, but rather just 3. That the set was closed under vector addition, scale multiplication, and that 0 was in the set. And if those 3 things were true, then our subset would become a vector space by itself. So, for example, I will state that the set of all continuous functions is a vector space. The set of all continuous functions. So polynomials, exponentials, trig function, all of those types of functions are continuous. We put all of them together, we form this vector space. Now the set of all polynomials of degree 2 or less is a subset within that larger vector space. So here is the set of all continuous functions. And here is some small subset of all polynomials of degree 2 or less. And so the question, is this subset actually a vector space? So that's the question. We'll start with yes or no. Go ahead and type your answer into the chat. Yes, it's a subspace. No, it's not a subspace. Or a question mark. Totally fine answer as well. All right, a whole bunch of yeses so far, and it is a vector space, and we can really show it holds all those things. So in general, we have our general polynomial that looks like ax squared plus bx plus c. And the idea is if I looked at 0x squared plus 0x plus 0, I could add that polynomial to any other polynomial, and it wouldn't change its identity. This is what we mean by the 0 vector. So this would be a 0 vector in that space. If I take any two polynomials, if I take any two random one, 3x squared plus 4x plus 10, and I add it to some other polynomial, I'm going to get a polynomial of degree 2 or less. So no matter what two I add together, I will still have a polynomial of degree 2 or less, so it's closed under vector addition. And similarly, if I take my random polynomial and I multiply this guy by 100 or any other scalar, the result is still going to be a polynomial of degree 2 or less. So it satisfies all 3 of those properties. So we could say it's a vector space. And the reason we wanted to categorize sets as vector spaces is because vector spaces had some key characteristics, one of which was that it has a basis. Every vector space has a basis and a dimension. And so we're going to remind ourselves of some vocab. A base is a set of linearly independent vectors that span a space. And it's always rough when we have vocab words inside of vocab words. So spanning the space means that the set of all linear combinations, remember the set of all linear combinations is the span of a set of vectors. If the span includes every vector in the space, then we would say the set is spanning the space. Basically, this means that I can build any vector in the vector space using just my basic vectors. They also are required to be linearly independent, which means that none of the vectors can be written as a linear combination of the other vectors. In other words, I don't have any extra vectors. It's the smallest set I can build the whole space with. And then we have the idea of dimension. The number of vectors in the basis is called the dimension of a space. So we have a definition of basis, dimension, and a little sub-vocabulary there. So our next question is if I'm working in the set of all polynomials of degree 2 or less, now we've established that's a vector space. Here I have a list of 4 vectors in that space. Is that set of vectors a basis for the vector space? Once again, yes or no? Is this a basis for the vector space? Looking for a reply from everyone. Yes, no, question mark. All right, couple answers so far. All right. All right, so 2 questions. Does this set of 4 vectors span the space, and is it linearly independent? So, in other words, could I build any second-degree polynomial using these 4 vectors? And I feel like I can. I feel like if I take some number of these, I can kind of control the constant value, plus some number of here, I can kind of control that x value, plus some number of this one, I could control the x squared component. So I feel like I could build any polynomial using these 4 vectors. However, if I give them names, if I call them B1 vector, B2 vector, B3 vector, and B4 vector, what I see is that if I take B1 plus B3, I get B4. So that tells me B4 is just a linear combination of B1 and B3. B4 is kind of like an extra vector. I actually don't need it to build all of the vector space. So in this case, this set of 4 vectors is linearly dependent and would not be a basis. However, if I removed B4 and just looked at the set of vectors B1, B2, and B3, that would be a basis. That would be a basis for our vector space P2. Okay. Having established that that's a basis, what is the dimension of the vector space? Go ahead and type that into the chat. What is the dimension of this vector space? All right. Quite a few threes real quick. So our definition of basis is, our dimension is the number of vectors in this basis. Here's a basis. I have 3 vectors in it, so the dimension is 3. Next, because this is a basis, I should be able to build any vector in the space. So if this is an example of one vector in this vector space, one polynomial in this function space, I should be able to build it using my basis vectors. In other words, I should be able to take a linear combination of my basis vectors and build any vector, including this vector v. And in that case, I should be able to find the coordinates of v in terms of the beta basis. So next question, go ahead and calculate these coordinates and type those into the chat. What are the coordinates of v in the beta basis? And I'm going to call this my beta basis. right, a couple answers in so far. Let's take a look. So the coordinates are how much of each basis vector I need to build the vector v. So in this case, I'm trying to build the vector 4x squared plus x plus 3. And so my first basis vector is constant 1. And then I would have this one's my second basis vector, and this one would be my third. And I'm actually going to start maybe with that third piece there. All right, so if I have b3 is equal to 2x squared, and I need to get to 4x squared, it looks like I'm going to need 2 of those b3s. That should give me my 4x squared. And I need to generate one x value, so I'm going to need 1 of the b2 vectors. And that should generate a x minus 1 for me. So now I have my constant x. But now I need a constant value of 3, and I already have a negative 1, so it looks like I'm going to need 4 of my first basis vector, and then that 4 times 1 minus 1 will end up to be 3. So I need 4 of the first basis vector, 1 of the second basis vector, 2 of the third basis vector to generate my vector v. So I would say the coordinates are 4, 1, 2. How much of each basis vector I need to build a space. All right, any questions here about basis or coordinates? All right. So next we're going to look at some potential other vector spaces. So if we have a matrix equation, AX equals B for some 4 by 3 matrix and some non-zero vector B, does the solutions to this matrix equation form a vector space? So do the solutions to AX equals B form a vector space? Yes or no? All right, a couple quick questions in the chat, or quick answers in the chat there. So I'm thinking about the solutions to AX equals B, right? So my x vector is a 3 by 1 vector. So all of my vectors x will live in, there'll be a subspace of R3. All of my x's live in R3. So the subset that is just the solutions to the equation, the question is, does that subset form a vector space? And I have to check my 3 criteria. So one is the 0 vector in the space? So this question would be, is 0 a solution to AX equals B? Well, unfortunately, A times 0 equals 0, which is not necessarily B. So that first condition is not satisfied, so this set of all solutions AX equals B will not form a vector space. In fact, it also fails the other two conditions as well. So it's also not closed under vector addition or scalar multiplication. So the solutions to AX equals B are not a vector space. However, if we look at the solutions to AX equals 0, this will form a vector space. We can see that 0 is a solution, therefore 0 is in the space. If I let x1 and x2, these two vectors, both be solutions, any two solutions, i.e. if a times x1 was equal to 0 and a times x2 was equal to 0, then if we took the sum of any two solutions, any two vectors in our space, and added them together, would the sum also be a solution? And if we multiplied that by a and distributed, we would get 0 plus 0, which would equal 0. So it tells me if I take any two vectors in the space, I add them together, I still have another solution. I still have a vector in the space. So it's closed under vector addition. And we could show that it's also closed under scalar multiplication as well. So the set of all solutions to AX equals B was not a vector space, but the set of all solutions to ax equals 0, the homogeneous equation, is a vector space. In fact, it's kind of a famous vector space, and we have a fancy name for it. What is the name of this vector space? The set of all
Null space.
Absolutely, the null space. So this is the null space. Okay, so we have two matrix spaces associated with the matrix A. One is the null space, one is the column space. The null space is the set of all solutions to the homogeneous equation, ax equals 0. And the column space is the set of all linear combinations of the columns of A. It's the span of the columns. So the null space are just the x's that map to 0, right? So it's some subset of the x's. The column space is the span of the columns. So if we think of taking A times some x to generate some B, right, all of the outputs, all of the b's in ax equals b would represent the column space. So given some matrix A, we should already know the dimensions of x and the dimensions of b. So we should know that the null space is a subset of what larger vector space, and the column space is a subspace of a larger vector space. So for instance, here's my matrix M, and I see that all of the columns of M are vectors that live in R3. So if I take linear combinations of the columns to form the column space, all of those vectors will also be in R3. So the column space is a subspace of R3. The null space are the solutions to ax equals 0. Just for me to be able to multiply this M by some vector x, x would have to be a vector in R6. So the null space, which is just the x's that map to 0, but it must be a subset of R6. And these are both going to be not only subsets, but subspaces, which means they're also going to be able to have a basis and a dimension of each, and we should be able to find those. So the next question is, consider this matrix, which row reduces to the following form. Answer these four questions really. The column space is a subset of what larger space, the null space is a subset of what larger space, and find a basis for each. Go ahead and see if we can work through these questions. And when you're all done, we'll add one more question here. We'll also say the dimension of the null space of A is equal to what? Go ahead and type that number into the chat when you're all done. See if you can answer all these questions. When you're all done, type your answer to the dimension of the null space into the chat. Answers so far. We wait for one or two more. Answer all these questions and then put the dimension of the null space into the chat. let's take a look. All right, so the column space is a subspace of what larger vector space. Well, in this case, all of the columns are vectors that live in R2. And so if I take linear combinations, the result will also be in R2. So the column space is a subset of R2. Now, since this matrix is a 2 by 4 matrix, the vector x would have to be a 4 by 1 vector to do the multiplication, which tells me the null space is a subset of R4. All of my x vectors will live in R4. Now we need to find a basis for the column space. A base is a set of vectors, the smallest set of vectors I can build the entire space with. Say a linearly independent set of vectors that span a space. I know I can build the column space using the 4 columns. That's the definition. But I need a linearly independent set. So I need the linearly independent columns of A for the basis of the column space. To find out which vectors are linearly independent, I would do the row reduction. I would then identify the pivots. Because there's a pivot in column 1 and column 3, I would take column 1 and column 3 of the associated matrix A. So the basis for the column space, A basis for the column space, would be 1, 1, and 1, 2. Because there are 2 vectors in the basis, the rank of A, which is just a fancy name for the dimension of the column space, would be equal to 2. In this case, the column space is a 2-dimensional subspace of R2, which basically means is all of R2. Any questions about column space? And then we look at the null space. The null space is the solutions to AX equals 0. So to find a basis, we're going to solve AX equals 0. To do that, I would take my matrix, I would augment with 0 and do the row reduction. And the result would be this. From there, I'm going to write my solution in parametric vector form. So I write the first equation as x1 equals minus 2x2 minus x4 when I subtract those values to the other side. I know that x2 is a free variable since there's no pivot in the x2 column. The second row tells me that x3 is equal to negative x4, and there's no pivot in the x4 column, so x4 is free. In parametric vector form, this looks like negative 2, 1, 0, 0 times x2 plus x4 times the vector negative 1, 0, negative 1, 1. So that means I can build all of the vectors in the null space by taking a linear combination of these 2 linearly independent vectors. Therefore, the basis for the null space would be these 2 vectors. In this case, there are 2 vectors in this basis, so the dimension of the null space is 2. In this case, the null space is a 2-dimensional subspace of R4. It's like a plane in R4. Any questions here about a null space? All right. Now, one application of null space that we didn't really have time to talk about in class, I'm only going to briefly mention here, is that they're super important in the theory of differential equations, a following course. And the reason they're important is because we're going to use them when we talk about the solution of a homogeneous differential equation, which is a fancy differential equation that looks like this. Now, it turns out in that class, we'll learn how to rewrite a differential equation by using a linear operator. And so we can really rewrite a differential equation as essentially a homogeneous linear transformation, which means the solutions will form a vector space. In this case, the solutions form a 2-dimensional vector space, which means any solution should be able to be represented as a linear combination of its 2 basis vectors. And so in a differential equations class, you'll learn some tricks to find 2 linearly independent solutions, and then you'll use your theory to say that this is the general solution. So this is really the main idea behind the null spaces when we generalize it to functions. Don't worry, that, however, will not be on the exam. All right, as we wrapped up chapter 2, we got into chapter 3, which is on determinants. We talked about determinants, and you should be able to calculate a 2 by 2 determinant using our formula. What is the determinant of this matrix right here? Go ahead and type that in the chat. It's the determinant of this matrix, 1, 2, 3, 7. All right, seeing a couple quick calculations. Perfect. So the determinant here is the product of the strong diagonal, 1 times 7, minus the product of the off diagonal, 2 times 3. We get a value of 1. So we have that nice formula for the determinant of a 2 by 2. For the determinant of a larger matrix, we have to do an expansion along a row or a column. So in other words, if I chose to expand along the first column, as I move across on the first row, as I move across that first row, at every position, I will get a sign, a number, and a subdeterminant. So to expand along the first row, I would fix my signs, positive, negative, as they alternate across my row. I would have plus 2 times the determinant I get when I eliminate the row and column of the 2. So times the subdeterminant. That looks like this. Then I would have minus 1 times the subdeterminant. That looks like this. Then plus 0 times some subdeterminant, and then minus 3 times the subdeterminant. I would get when I eliminate the row and column of the 3. So this would be 0, 0, 1, 1, 3, 4, 0, 0, 3. Now, having done my expansion, I've reduced the determinant of one 4 by 4 matrix to 3 determinants of 3 by 3s. And I would repeat that process to whittle these 3 by 3s down to 2 by 2s, and then finally I would generate the number. Now we noticed when we did that row expansion that this term was very nice because the number corresponding to that location was 0. So in general, it's good practice to expand along the row or column with the most zeros. So in other words, instead of doing this calculation, if I had instead chose to expand across the second row, I would fix my signs, positive in the top left, alternating as I move through the matrix. And I would basically get minus 0 times the determinant, plus 0 times the determinant. And eventually I would get minus 1 times the subdeterminant. When I eliminate the column and row of the 1, and I would be left with 2, 1, 3, 1, 3, 2, 0, 0, 4. By choosing the proper row, I only have to do one 3 by 3 determinant instead of 3. And then from here, I would want to expand along the third row because there's more zeros in that row. In this case, I would get my negative 1. I would go plus, minus, plus, minus, plus. And I would get 4 times the subdeterminant, 2, 1, 1, 3. I would get negative 4 times 6 minus 1. I would get a value of negative 20. So that's our process for row expansion, and an emphasis on choosing the row or column with the most zeros. Any questions about that determinant calculation? All right, so we need to know how to calculate determinants, and we need to know their properties. So these are some key properties. If I know the determinant of A is equal to negative 2, and the determinant of B is equal to 6, go ahead and calculate these values. Why don't we just enter this first one into the chat? What's the determinant of A times B? The determinant of A is negative 2, and the determinant of B is 6. What's the determinant of A times B? All right, perfect. Couple of responses. So we have a property says that the determinant of the product is the product of the determinants. In other words, this is equal to the determinant of A times the determinant of B. so this is equal to negative 12. We have a property that says the determinant of A transpose is just equal to the determinant of A. Remember, the transpose just flips the rows and columns, and since I can expand along any row or column to calculate a determinant, the value should come out the same. Now, the determinant of 2A can be a little bit tricky. In this case, we have a 4 by 4 matrix. If I multiplied one row of the matrix A by 2, I would have to double the associated determinant. But when I take 2 times the entire matrix A, I am multiplying all 4 of those rows by A. So that means my answer here should be 2 to the 4th power times the determinant of A. So in this case, my answer would be negative 32. 2, 4, 8, 16, yep, 32. All right, next, if a matrix A is triangular, then the determinant is the product of the diagonal entries. And this can be a real time saver. In other words, if I want to calculate the determinant of the matrix 1, 7, 19, 0, 2, 14, 0, 0, negative 3, the determinant is just the product of the diagonal entries. 1 times 2 times negative 3, which would be negative 6. That's true for any triangular matrix. And then lastly, an important property is the matrix A is invertible if and only if the determinant is not equal to 0, right? So we have a formula, another property that says the determinant of A inverse is equal to 1 over the determinant of A. And using that property, we can see that if the determinant of A is 0, then we couldn't calculate the determinant of inverse because there would exist no inverse. So if the determinant of A is 0, matrix A is not invertible, or the way we phrase it here is the matrix is invertible if and only if the determinant is not equal to 0. Now, where this property is very useful to us, where we really use this, is when it's related to a homogeneous equation. So if we think about the homogeneous equation, AX equals 0, I know there's a solution to that equation. I know that if I plug in X equals 0, that will be a solution. So I'm usually only interested in the non-trivial solutions of this equation. I would say that the homogeneous equation has non-trivial solutions other than 0, if and only if A is not invertible. If A was invertible, I would multiply both sides by the inverse, I would get X equals 0, and that would be the only solution. So there's other solutions only if A is not invertible, and that happens if and only if the determinant of A is equal to 0. So now I can say that AX equals 0 has non-trivial solutions whenever the determinant of A is equal to 0. And this little chain of logic will be important as we discuss eigenvalues and eigenvectors. So the big idea of eigenvalues and eigenvectors is this. The concept is it's a relationship where A times a vector is somehow equal to just a scaling of that vector. Right? That action is true. That's the most important concept of eigenvalues, eigenvectors. But then we actually want to solve to find out what x and lambda are. And so we work with our original equation. Maybe we subtract this to the other side. Maybe we factor out that x, and we can rewrite that as a homogeneous equation. The problem is I can't solve this equation because I have two unknowns, lambda and x, and I only have one equation. But I'm looking for non-zero solutions to this homogeneous equation. And that can only happen if this matrix is not invertible, which can only happen when the determinant of that matrix is equal to 0. I like this equation because there's only one unknown, and I can solve that for lambda. And that brings us to our general process. Step 1 says solve that determinant equation to find your eigenvalues. Once we know the eigenvalues, We can then plug those into our homogeneous matrix equation to solve for the associated eigenvectors. So that is our general process. Let's see if we can knock one out. Go ahead and calculate the eigenvalues and eigenvectors for this matrix. Once you find your eigenvalues, why don't you type your eigenvalues into the chat, just to make sure we're all working with the correct eigenvalues. So I see a lot of eigenvalues in the chat, 2, -1. I agree with those values. My work is on the screen. Those look good. Go ahead and calculate the eigenvectors. Once you have your eigenvectors, go ahead and type those into the chat. Couple answers in the chat. I'm going to start working through my solution. My first step was to find the eigenvalues. So I subtracted lambda on the diagonal, and I calculated the determinant. That resulted in the characteristic equation, characteristic polynomial, which in this case, because I had a 2 by 2 matrix, was a second-degree polynomial. I was able to factor the polynomial to find the root values, lambda equals 2 and -1. If I didn't see the factorization, I could always use the quadratic formula. From here, I'm going to say if lambda equals 2, I will then solve my homogeneous matrix equation A minus lambda I times x equals 0, which is a homogeneous matrix equation. So I take A and I subtract 2 on the diagonal, augment with 0, and I do my row reduction. In this case, if I take row 2 plus row 1, I'll get a row of all zeros, and then I'll multiply row 1 by -1. And there's my row reduced matrix. From here, I write my solution in parametric vector form, x2 being my free variable, and I get the associated eigenvector 2, 1. So my first eigenpair is lambda equals 2, with the associated eigenvector 2, 1. And now I repeat that process with the other eigenvalue. I say if lambda equals -1, subtracting -1 on the diagonal would be 2, 2, 1, 1, augmented with 0. In this case, I'm going to divide the first row by 2. I'll get 1, 1, 0. And then I'll take the second row minus this row to get a row of all zeros. So that would be my row reduction here. From here, I have x1 equals -x2, and I subtract that x2 to the other side. And x2 is my free variable. So in this time, my eigenvector is going to be -1, 1. So my second eigenpair is when lambda equals -1. The associated eigenvector is -1, 1. So now I have my eigenvalues and eigenvectors. Any questions on these calculations?
Yeah, for the test, you know how sometimes eigenvectors come out like 3/2, 1, something like that. Do you want us to convert that to a more like regular looking one, or are you okay with having fractions in your eigenvectors for the test?
It's totally fine to have fractions on the eigenvectors on the
Okay.
test, right? You can really leave them any form. I personally like to clear them because I hate fractions, but totally fine to enter them in here.
Okay.
Okay, so now we talk about the application of eigenvalues and eigenvectors. And one of the applications is factorization of the matrix A into PDP inverse, or the diagonalization of the matrix A. Now to factor A, the matrix P turns out to have columns that are the eigenvectors. So the columns of A, the eigenvectors of A are the columns of the matrix P. The matrix D is a diagonal matrix, and the diagonal entries are the eigenvalues of A. So all of the work in the diagonalization process is really just in calculating the eigenvalues and eigenvectors. So for instance, if I look at my above matrix A, I could factor it into PDP inverse, and I would take my eigenvectors to be the columns of P. So my first eigenvector would be the first column, the second eigenvector would be the second column, and then my matrix D would be the diagonal matrix, where the eigenvalues were the diagonal entry, and that should be -1 there. And then lastly, once I know what P is, I can calculate P inverse. In this case, it would be 1 over 2 minus -1 times the matrix I get when I switch the values on the strong diagonal and change the signs on the off diagonal. And so this would be my factorization of A into PDP inverse. Any questions on the matrix factorization? So now we know how to calculate the eigenvalues and eigenvectors and how to diagonalize the matrix. One question would be, can we always do this? When can we diagonalize a matrix? And the next question would be, why do we want to? All right, so we know that we will go to calculate the eigenvalues. When we calculate this determinant, we're going to get an nth degree polynomial. That nth degree polynomial will always have n roots. Now, in the case where we have distinct roots, for instance, if we have lambda equals 1, 2, and 3, in this case, we are going to generate 3 associated eigenvectors. We'll get eigenvectors 1, 2, 3, 4, 5, 6, and 7, 8, 9 for maybe examples, kind of a made-up example. But if 3 different eigenvalues are going to give me 3 different eigenvectors. In this case, I will always be able to take those eigenvectors and form a square matrix P, which is invertible, and I will be able to diagonalize. However, if I have repeated roots, in other words, now I have lambda equals 1, 2, and 2, for instance, where the eigenvalue 2 is repeated, I know that when I plug in lambda equals 1, I will generate 1 eigenvector. But I'm not sure what happens when I plug in lambda equals 2. Sometimes I might only get 1 eigenvector. If that's the case, then I cannot form a square matrix P, and therefore the matrix A is not diagonalizable. However, in other cases, when I plug in lambda equals 2, I will have 2 free variables in my solution process, and I will be able to generate a second eigenvector. In that case, my matrix is diagonalizable. So the question about diagonalizability is really, am I going to get enough eigenvectors from the repeated eigenvalues? Now, the number of times that the eigenvalue is repeated is called the algebraic multiplicity, and the number of associated eigenvectors that we get, or a better way to say that is the dimension of the associated eigenspace, is called the geometric multiplicity. And so more formally, we could say that the matrix is diagonalizable if the geometric multiplicity is equal to the algebraic multiplicity for all the eigenpairs. All right, our last case is the complex Ruts. If I have eigenvalues lambda equals a minus bi and a plus bi, and the associated eigenvector, then instead of diagonalizing, where we'd have complex values on the diagonal, instead we focus on a factorization PCP inverse, where in this case, the matrix P, the columns of P, the first column would be the real parts of the eigenvector, and the second column would be the imaginary parts of the eigenvector, and the matrix C would be a rotational matrix with this formula here. And remember, these are the associated formulas when we use the negative eigenvalue and its associated eigenvector. So, given this review, we're going to look at this first matrix and determine if that matrix is diagonalizable. So say yes or no, this matrix is diagonalizable. Type that in the chat. Is this matrix diagonalizable? All right, let's take a look. Well, the nice thing about this matrix is that it is a triangular matrix. Because it's triangular, I know that the eigenvalues will just be the diagonal entries. So I immediately can see that the eigenvalues are 1, 2, and 2. I know that if I plug in lambda equals 1, I will generate one eigenvector. The only question is, how many eigenvectors will I get when I plug in lambda equals 2? So I'm going to check that case. I'm going to say if lambda equals 2, I'm then going to solve the associated homogeneous equation. So I subtract 2 on the diagonal, and I do my row reduction. In this case, I'm going to, and I probably should augment with 0. I don't have to show that, but I like to augment with 0, so it reminds me of what I'm really doing here. I'm going to multiply the second row by 1/2, and then take row 2 minus row 1 to get zeros here and here, and multiply by a negative. So maybe I should show a couple of those steps, but basically I'm going to row reduce to this stage right here. Now here, I see there's only going to be one free variable, which means I'm going to only have one vector in my basis here. I'm going to get one eigenvector. So in this case, it's not going to be diagonalizable. To show that in more detail, I could write out the actual equations and find the eigenvector. I would have x1 is equal to 0, x3 is equal to 0, and x2 is a free variable. So in parametric vector form, my eigenvector is just 0, 1, 0. So I'll get one eigenvector from the eigenvalue 1, but I only get one eigenvector from lambda equals 2, which means I won't have enough eigenvectors to form a square matrix P. So in this case, it is not diagonalizable. Okay. Now the next case is going to have some complex Ruts, and we're going to do the associated PCP factorization. I'm just going to work through this one for the sake of time here. So step one is to calculate my eigenvalues. So I'm going to solve the determinant of a minus lambda I equals 0 for lambda. So I'm going to go 1 minus lambda, 5, negative 2, and 3 minus lambda. Calculate that determinant. Write out the definition of the determinant here. And then I'm going to say 1 times 3, 1 times negative lambda, negative 3 lambda, plus lambda squared, plus 10. I'm going to get lambda squared minus 4 lambda plus 13 equals 0. And then I'm going to try to factor it. I'm going to look at it. I know the factors of 13 are only 1 and 13. I really can't use those to create a negative 4. So after staring at it for a little bit, I'm going to have to use the quadratic formula. So my quadratic formula, which we're going to need to know, negative b plus or minus the square root of b squared minus 4ac all over 2a. Now I plug in my values. I will get 4 plus or minus the square root of 16 minus 4 times 13, which is 52, all over 2. 2 plus or minus. Looks like 16 minus 52 is going to be negative 36, and the square root of negative 36 is going to be 6i. So it looks like I have 2 plus or minus 3i as my eigenvalues. Now from here, I'm going to calculate my eigenvector. And I'm going to do it a little bit differently, actually, than I did it in the instructional video. I think this newer process is a little more straightforward. So I'm going to let lambda equal 2 minus 3i. There's my eigenvalue. And just like I would any other time, I'm going to take my matrix. I'm going to subtract my eigenvalue, 2 minus 3i on the diagonal. I'm going to augment with 0. I'm going to do my row reduction. The first step is to simplify this a little bit. Negative 1 plus 3i when I distribute the negative. And then I'll have 1 plus 3i augmented with 0. All right. Now I'm going to go through this the long way, but there is a shortcut that we could go right from this stage to make this a little bit easier. What I'm going to do instead is I'm going to continue my row reduction. I'm going to try to get a 1 in this position. So I'm going to multiply through by the conjugate of that value. Conjugate of that first complex value. I'm going to have negative 1 plus 3i times negative 1 minus 3i. When I multiply those together, I'm going to get 1 plus 3i minus 3i minus 3i squared, which is 9i squared. And I squared is negative 1, so this is actually going to result in the number 10. So when you multiply a complex number by its conjugate, you get a real number. My second component will be 5 times negative 1 minus 3i. All right. I'm going to do one more operation here, which is going to be slightly weird. I'm going to take negative 1/5 times row 1. And when I do that, I'm going to get negative 2. I'm going to get negative 1 times this stuff, and I'll distribute that negative 1 to get 1 plus 3i augmented with 0. And then my second row is still this. In going through that row reduction process, I can now see that the second row and first row are the same. And now I would take row 2 minus row 1 to get a row of zeros. And that would bring me to this stage right here. And what I would say is that I actually don't have to go through that process because in a 2 by 2 system, I know these two rows have to be multiples of each other for there to be a non-zero eigenvector. I've chosen lambda, so this has to happen. So when I get to this stage, I could just choose the second row and assume it can eliminate the first row. And so you can jump right from that stage to this stage if you like. Now from here, I'm just going to finish the row reduction like I would for any other problem. I'll take negative 1/2 times row 1. I'll get 1 minus 1/2 minus 3/2 I augmented with 0. I'll write out the equation associated with that row. x1, I'll add that to the, subtract that to the other side to get positive 1/2 plus 3/2 I all times x2, and x2 will be my free variable. In parametric vector form, I would have x2 times the vector 1/2 plus 3/2 I and 1. And that would be a perfectly good eigenvector. Give myself a little more room here. I'm going to write my eigenvalue here, which is 2 minus 3i. And my associated eigenvector, which I'm going to multiply by 2 just to clear my fractions, will be 1 plus 3i and 2. Once again, you don't have to do that. I'm choosing to do that here. And there I have calculated my complex eigenvalue eigenvector. Now I don't have to calculate the second one. I know what the second one will be. I know that if I use the conjugate eigenvalue, that the eigenvector will be the conjugate eigenvector. So I just get that one for free. Any questions here about calculating complex eigenvalues and eigenvectors? All right. My last step then is to write out the factorization. There we go. So I know that because I have complex eigenvalues that I should be able to factor A into P, C, P inverse. Now to form P, I'm just going to look at one eigenpair, not both eigenpairs, but just the one with the negative eigenvalue. Using that eigenvector, I'm going to take the real parts, 1 and 2 as the first column, and the imaginary parts, 3 and 0, as the second column. And that's my matrix P. My matrix C is going to have the form A negative B, B, A, where the A and V values are the real and imaginary parts of the eigenvalue, 2 and 3. And if you choose the negative eigenvalue, your negative sign will always go in the top right corner. And then once I know what P is, I could calculate P inverse if I want. And so that should be the factorization PCP inverse. All right, the last piece is applications of eigenvectors. And there's really two we looked at in class. One is raising powers, matrix powers. So given a matrix A, if I wanted to calculate A to the 10th, in general, that would be hard to do. I'd have to take A times A times A 10 times. However, if I have a diagonal matrix D, raising that to the 10th power is much easier because I can just raise the diagonal components to that 10th power. That's only true for a diagonal matrix. So if I have A factoring into P D P inverse, it turns out A to the 10th will be P D to the 10th P inverse. And in class with the derivation of where that came from in one of the videos. So in this case, I could write an expression for A to the 10th by just calculating the product of these 3 matrices instead of those 10 matrices. So that's one application, is that it allows us a more efficient way to calculate the powers of a matrix. The next application was dynamic systems. And the dynamic systems is really coming from that Mathematica lab notebook where it was introduced. And the big idea is where a dynamic system just starts at some initial condition, some initial state of a system, x sub 0. And then multiplying that by some matrix A, we get to the next state of the system. And to get to the next state, we'd be multiplying A by again, and again, and again, and again, and again. And it turns out that if we use the eigenvectors of A as a basis for our space, then we can write a formula for the kth state of the system in terms of the eigenvalues and eigenvectors. And I should probably not mix notation. Let's call my eigenvectors V's instead of X's. Okay. All right, and this is a really important application. You'll see in lots of different areas, dynamic systems. And it was introduced in the lab, but it will not be on the exam. So don't worry too much if you have kind of a cloudy understanding of that. Make sure we can get through those eigenvalues and eigenvector calculations, and I won't put this on the exam. All right, that really wraps up the review session. Any last questions at all for me?
Wait, so the power thing that you just talked about that's not going to be on the exam?
So this has the potential to be on there, the powers, but not the dynamic systems. There won't be any questions for the dynamic systems. So you saw some questions on the homework about the dynamic systems. You won't have those questions on the exam.
Okay, got it. Thanks.
Any other questions? All right, that concludes this review session. Thank you very much for coming. Let me know if you have any questions for the exam.